In this module, we're going to examine various scanning procedures. We'll look at scanning against networks, individual hosts and ports, as well as discovering the operating system running on a target. We'll also look at tactics for avoiding security appliances during scanning and the importance of creating network maps using our gathered intelligence. As we move into the network scanning phase, let's take a survey of some of the most popular network scanning tools that you're likely to use during your assessment. As we've done previously, we're going to use mainly here a tool from Parrot OS, which is Nmap. We've worked through our reconnaissance phase already, which is phase 1 of our hacking methodology, where we used footprinting techniques to gather information about a potential target. Using the information found during that initial phase, we would then move to phase 2, and we would begin looking for even more information about the target through scanning and actually interacting with the target in several ways. So although this phase is similar in that we are still gathering intelligence, this is where we actually start to engage more and we actually interact with a target. So again, let's start with one of the most well-known tools, which is Nmap. Nmap will allow you to discover lots of information about a target, including the various hosts that are available on a given subnet, the services running, and the available ports which are open. And this essentially gives us a virtual map of the network. Nmap has lots of different tools and functions to perform this, so let's take a look at a few of those options. Now, just like many things here in this course, Nmap is very, very extensive. It is so powerful with many optional parameters that we just can't possibly cover all of those. However, the nmap.org site has a wonderful reference guide that we can pull up here, and that's going to give us a lot more information. Definitely check that out if you want to get in depth with this tool. Here on the nmap.org site, in the left menu, we see a link to the reference guide, which is what we're currently looking at. And from here, you're going to see information about various commands and syntax options. Also, if we jump back into our Parrot terminal here, and we use the nmap command and hit enter, you'll notice at the bottom of this command output, we also see a message here letting us know where we can reference the manual page. And again, that is the same website that we just looked at. That's going to provide more options and more examples of Nmap usage. So let's say that we have chosen a target network and we have an IP address range. In my case, I'm going to just use the local network that my virtual machines are on. If I clear this off and I perform an ifconfig command, we're going to see my local IP address, which we see here. The inet address is 10.0.2.15. And we see that I am on a /24 network. In other words, 255.255.255.0. So my local network is 10.0.2.0/24. And my local IP address for this virtual machine is 10.0.2.15. So let's assume in this case that this is the target subnet against which we want to perform some testing. Now, before we get up and going, let me show you another tool I use called OWASP Broken Web Applications, or OWASP BWA for short. You can see here the SourceForge project page for this tool, which will allow you to download the OVA file for installation in a virtual machine. So I already have this downloaded. I've installed that as a virtual machine just as I have with my Parrot OS, and they are on the same subnet. This particular virtual machine was created by OWASP, which is the Open Web Application Security Project. And this is a way that we can test our skills. This is a collection of purposefully vulnerable web apps that you can test against. So this is a great free tool, and it's something that I use quite often. Now, you'll also notice that the last update was in 2016, so it's not particularly new. This is version 1.2, and that's totally okay. This is just an intentionally vulnerable VM that will allow us to do some testing, so it doesn't really matter that it's not particularly recent. Again, to save time, I do already have this installed. So if I pull that over into my main window, this is my OWASP BWA virtual machine. This is Ubuntu based, and it's going to present a terminal once you install that completely, just as we see here. It is fairly small and it's really fast to install. So if I say ifconfig in this virtual machine, you'll see that it has the local IP address 10.0.2.4. And again, that is a /24 subnet mask. So this is, in fact, on the same subnet as my parent OS. This IP address, this 10.0.2.4, this is how we can access the vulnerable web applications from a browser. So if I jump back over to my parent OS instance and I go out to that IP address, 10.0.2.4, you'll see that this will launch my OWASP BWA web app page. And you can see a list of all of the various training applications that are included with this VM. We'll dive into that more later on, but for now, I wanted to make you aware of this tool and show you where some of our Nmap scanning results are going to come from, which is this particular VM. We're going to scan against this subnet, and this VM is the only other machine on this subnet at the moment. So let's minimize this. And let's go back into my terminal here, and let's clear this off. And one of the most basic functions for Nmap is to identify active hosts on a network. We can do that with a simple ping scan in Nmap. And we can say nmap-sn, which indicates we don't want to do a port scan, only a ping sweep. And we follow that with the target IP address or a target range. In my case, I'm going to use a range, the entire subnet, 10.0.2.0/24, and I'm going to hit enter. So this is actively trying to ping every IP address that is found within that subnet range. And once this is done, it will take just a bit of time to complete. We'll see a list of all of the hosts which are up on that network. And so we see that here. And of course, my only host is the 10.0.2.4, which is a virtual NIC in my VirtualBox instance. We see our own local adapter as well, 10.0.2.15. We see the results letting us know that 5 hosts are up. These are, of course, some other virtual NICs that I have running. And so that's how we can do a quick ping sweep using Nmap. That's one of the most common ways that we might do that, looking for hosts that may be alive on a network. Now let's talk also about how we can do a port scan with Nmap as well. Remember, we've talked about how finding open ports can oftentimes provide a window into a system or a network, and Nmap is a great way that we can do that. I've also already mentioned, just like with many tools in this course, Nmap is very extensive, it's very powerful, it has all kinds of optional parameters, and we just can't possibly cover all of those. However, that nmap.org website is going to have the reference guide that's going to explain all kinds of usage. Definitely check that out, but let's look at one of the most common usages here for port scanning. First, let's choose one of the hosts from our lists. Let's say we performed a ping sweep against a subnet. We have a list of interesting hosts provided to us here, and maybe we want to choose one of those for a more targeted scan. In my case, I'm going to choose the 10.0.2.4 IP address, which is of course my OWASP BWA virtual machine. So let's start with the nmap command, and I'm going to follow that with the -A optional parameter. That's going to tell Nmap, I want you to show me all of the information about this that you can possibly gather. And I'm also going to say -T 5. This is the speed at which we're going to perform the scan. Now, in the real world, you want to be careful here. The speed that you can run Nmap ranges from 1 through 5, and for the purposes of this lab, I can go all out most of the time. I can go full speed, but in the real world, there are often mechanisms in place that are going to look for highly repetitious actions on the network, so you can potentially give yourself away if you do this. Not only that, but you can potentially miss something as well, so just be aware of that. And I'm going to end with the IP address 10.0.2.4. I'm going to hit enter, and once this completes, it's going to display the results from the top 1,000 most common ports, which would be ports like 80, 443, port 22, and so on. And this will take just a bit of time to complete for us, considerably longer than it took for the initial ping sweep. So I'm actually going to pause the recording here, and I'll resume once this process is completed. Okay, now you can see that our output is complete, and if I scroll up, you can see the enormous amount of information that we have presented to us here. We can scroll all the way up to the top and start taking a look at some of these. We see port 22 for TCP is open using the SSH service. We also see port 80 for TCP is open as well. we see port 139 open for TCP, which is Samba file sharing. We see port 143 for IMAP is also open. We see port 443 open as well using HTTPS, and we even see information about the certificate here. We see the common name for that. We see the validity dates. Further down, if we continue to scroll here, we're going to see things like our MAC address for our virtual NIC adapter that we see here, of course, using VirtualBox. So you can see an incredible amount of information here about one particular host, and that allows us to gather important data for further assessments. Now we can also scan for specific ports as well. If we go back down to the bottom of our output and we say nmap-p, which is going to indicate a specific port, and let's just say port 22, and we'll say 10.0.2.4, we'll hit enter, and we'll see a scan against only this port. So if we're interested in seeing if a specific port is open, in this case, port 22 for TCP using SSH, we can do that. That'll give us a faster output than scanning for all ports. We can also get more in-depth as well. We can say nmap-p-, which says I want to scan all of the ports available. Remember, we have over 65,000 ports available, so there's a large range that we aren't checking by default. So this says to check all of the potential ports. And one more parameter is -A, which says show me all of the possible information that you can gather. Protocol versions, fingerprints, everything you can gather, and we can say 10.0.2.4, and I'll hit enter. And once again, this will take quite some time to complete, so I'm going to pause the recording right here again, and we'll jump back in when this is finished up. Okay, now that Nmap scan is all complete, and you can see if we scroll up again the vast amount of information that we have here. This is a more detailed and verbose output for scanning against a specific port. So these are definitely things we would be interested in for further exploration. For completion, I also want to show you some other tools that you can use that aren't necessarily specific to Parrot OS, some free tools. Now let's jump out to our browser here. One of those is Angry IP Scanner. This is a free tool that can work on Mac OS, it can work on Windows, and they even have a mobile app. So this will perform a similar action of sweeping a particular subnet and showing you any hosts that seem to be up or alive. That's a free tool again. Another one is SolarWinds. They have a network device scanner. This particular tool comes with a free, fully functional 30-day trial, and you can see some of the more advanced features that are in that, including a visual map of the network, which is super handy to have. We have a product called Fing as well that I'll mention. Fing also is a tool that is available for desktop, or there's a mobile app. So if you're doing some mobile device testing, you might want to look towards one of these apps. If you're scanning against a wireless network and you don't happen to have a wireless adapter on your virtual machine, you can use one of these tools to try and find some hosts that may be in the upstate. And of course, this isn't an extensive list of tools available. There are certainly other free and paid tools out there that you can download, and even other options in Parrot OS, but these are certainly some of the most popular and widely used in the market. Now that we know about some network scanning tools, let's begin to look at a methodology for using these. The first place we would likely start is by using host discovery techniques, and we'll look at ways we can do this from Parrot OS. Some of this we've looked at briefly with Nmap already, but I want to go through a list of host discovery techniques that you'll want to use. Having a well thought out and methodical way to perform scanning is going to be very important if we want to be effective. So first off, let's begin with something basic, which is an ICMP scan. ICMP is something that you've likely used before, particularly if you come from a networking background, or if you're familiar with basic network troubleshooting. ICMP is a protocol that allows us to test the reachability of another device on the network. So for example, here in my terminal, if I say ping 10.0.2.4, you'll see that I am receiving responses from this ICMP ping. This command uses ICMP to see if this IP address is alive and able to respond to my own machine on the network. In this case, it is successful. We see those pings being returned here. And again, this IP address I'm using is my OWASP BWA virtual machine that I'm performing a ping against. If we want to perform this using Nmap, we can perform an ICMP scan against a particular target by saying nmap-sn, which indicates that we don't want to do a port scan, followed by -PE, which indicates that we are performing an ICMP echo ping scan. We would follow that with an IP address. In my case, I'll use 10.0.2.4 and I'll hit enter. When I do that, you can see the results here displaying the MAC address for the adapter from which we received an echo response. We can see the latency. We can see a message stating that the host is up as well. Optionally, in contrast to an ICMP scan, which is used for a specific host, we can do an ICMP sweep. A sweep, of course, is used for a range of IP addresses. So we can do that if I arrow up by saying nmap-sn-PE, and this time, instead of indicating a specific host, let's indicate the network, 10.0.2.0/24. I'll hit enter, and in the results of this, we're going to see a report, and now we see that displayed on our screen. We see that 256 IP addresses were scanned here. It let us know that 5 hosts were found to be in the upstate, and we similarly see the MAC addresses for each of these, as well as a message stating that they are in the upstate, and we see the latency for those packets as well. Another method for host discovery is something called an ARP scan. ARP stands for Address Resolution Protocol. This is used on networks to map IP addresses, which can change from time to time, to the permanent physical MAC address of a device. This is one of the most important protocols in networking that's used for communication. When we perform an ARP scan, we're going to send out ARP discovery packets for any device that is reachable. And one of the reasons this can be helpful for us is that most security appliances, such as firewalls, they will allow ARP packets to pass through even when other types of packets may be restricted. Just as with ping scans, if we get a response from an ARP scan, we know that the host is active on the network. In order to perform this, we say nmap-sn, once again indicating that we want to disable the port scan option, and we say -PR. This indicates that we want to perform an ARP scan, and we follow that with either the specific IP address or the IP address range. In my case, I'll do 10.0.2.4, and I'll hit enter, and we do see similar results here, letting us know that the host is up. So even though these results are similar, it is possible that if we scan against the entire network, we could get more information than we do from a ping scan. Again, this is particularly true if we have a security device in place which is denying ICMP packets on the network. We can also perform UDP and TCP scans as well. ICMP isn't associated with TCP or UDP. It's an entirely different function and protocol, so we can use those two options as a different way to test. UDP scans also help detect systems that may be behind a security appliance, such as a firewall. It's common for firewalls to filter TCP traffic, so this is a workaround for that. To do so, if we want to use a UDP scan, we can say nmap-sn-pu, and that indicates that we want to perform UDP scanning, and will indicate a specific IP address, 10.0.2.4. Here, once again, we'll hit enter, and we see similar results as we've seen before. As for TCP, we have a couple of options here for that. We can say nmap-sn-ps 10.0.2.4. I'll hit enter, and this will perform a TCP SYN ping scan. TCP uses a three-way handshake. When we're establishing a TCP session, we start by sending a SYN packet, and we wait to receive an ACK packet back as an acknowledgement. Then we'll respond with a final SYN ACK message to complete that handshake and establish a TCP session. When we use this nmap option, we're actually sending an empty TCP SYN packet over to the target host, and we're waiting to receive an ACK message as an acknowledgement. If we receive that message, this indicates that the host is in the upstate. As we see listed here, we're told that this particular host that we tested against is up. Nmap will then send a TCP reset packet to cancel the session establishment. Alternatively, if I arrow up, we can also say nmap-sn-pa against that same IP address, and I'll run that. This is a TCP ACK ping scan. This begins by sending an empty TCP ACK message over to the target, which causes the target to respond with its own reset message. The reset message lets us know that this host is up on the network. We can also use an optional parameter that will combine several protocols, and this is a somewhat newer option within Nmap. We can say nmap-sn, and we can say -po 10.0.2.4. The -po will send multiple IP packets over to the target. It will try TCP, UDP, ICMP, and even IGMP. A response to any of these packets will indicate that this particular host is up on the network, and we do see the results of that listed here in our output. As we looked at with our previous network scanning tools video, there are of course other standalone tool options that are point and click with a GUI which perform similar actions, and those would include tools such as Fing, SolarWinds, and Angry IP Scanner, among many others. Once we discover a particular target that is of interest to us on a network, we can move on from the host discovery methods into more specific discovery, beginning with port discovery. This will help us to learn about any ports that might be open and any services that may be running. This can give us an entry point into the target. With Nmap, this is really simple. We can simply say Nmap followed by the IP address. I can say 10.0.2.4 in my case, and pretty quickly we're going to see results from the 1,000 most popular ports listed in our Nmap services. We see results from SSH, we see HTTP, we see IMAP, and we see several others listed here. Now, if we want to expand this, if we want to go beyond those 1,000 most well-known ports, we can use an optional parameter. We can say nmap-p0- followed again by the IP address, 10.0.2.4 for me, and I'll hit enter to get that going. Now the P0 optional parameter, that tells Nmap that we want to go beyond those 1,000 most popular ports, and we want to expand our search into the entire port range. Now this will obviously take just a bit longer because we're scanning against many more ports, so we'll give that some time to complete, and then we'll take a look at that output. And now you can see our output. That took almost 30 seconds to run that scan. Now in my case, this did not reveal any additional ports outside of those that were already revealed in the default initial scan, but it is entirely possible that you do get some new results in a real-world test. So that's a general port discovery option. But we can also use specific protocol scanning as well. And most commonly, we'll do that through TCP. TCP is a reliable connection method, so that's a really good way to discover whether or not a port is open and what service might be running on that. We have a couple of options for TCP scanning. We have something called half open scanning and full open scanning. With a half open scan, we use the command nmap followed by lowercase s, capital S. The lowercase s says we're indicating a scanning option, and the uppercase S indicates that we want to use a half open scan, also referred to as a stealth scan, which is why we use an S. We follow that with a -v maybe, which means that we want to increase the verbosity level. We want to be more verbose in our output. In other words, we want more information returned. And I'll say 10.0.2.4, and I'll hit enter to get that up and going. And there you can see our output returned from that command, including the open port numbers that are using TCP. Now, as we looked at in a previous video, this is a method for prematurely terminating a TCP three-way handshake before that completes. And we do that in order to determine if a particular TCP port is open. The fact that this is terminating the three-way handshake before it is established is why we refer to this as a half-open scan. We're creating a half-open TCP connection. We're not completing the connection. We send out SYN packets over common TCP ports, and we wait to receive a TCP SYN ACK acknowledgement from the target. And then we will respond in turn with a TCP reset packet, which will cancel the TCP session establishment. As we mentioned, this can aid in bypassing restrictive firewalls. It can help us evade detection as well from various types of security appliances, maybe from an IPS. Optionally, we can perform a full open TCP scan. We can do that by saying nmap dash lowercase s capital T dash V, and I'll say 10.0.2.4, and I'll hit enter. The lowercase s capital T, of course, indicates that this is a full open TCP scan. Now, what we mean by full open is when we perform this type of scan, we're actually completing the three-way handshake briefly. We send out a send packet to begin session establishment. Then we wait to receive a send ACK packet as an acknowledgement. And then we respond with the appropriate ACK message, which completes the session establishment. Very shortly after this happens, we'll then send a TCP reset message, which will release the port and end the TCP session. So same principle, but slightly different execution. This method, this full open method, by the way, it is considered to be the more reliable way to scan for TCP because we're going through the complete three-way handshake for each appropriate port. We can also do something called a TCP ACK scan. This will help us to determine whether or not a target is behind a firewall. So if we say nmap dash lowercase s capital A to indicate a TCP ACK scan, and I'll say 10.0.2.4 and hit enter, and you'll be able to see our results here very quickly. Now, whether the port is open or whether it's closed, either way, the target is required to respond with a TCP reset message because we have used a random sequence number in the ACK message. If we don't receive any response at all, that would mean that a firewall has blocked the probe, or in other words, it's filtered the traffic. If, on the other hand, we do receive a TCP reset message, then this means our packet got all the way through to the target and no firewall is between us and the target that we've indicated. In the case of this output, you can see very explicitly stated here in this next to last line, all 1000 scanned ports on 10.0.2.4 are unfiltered. In other words, none of the ports on this target are behind a firewall, which is exactly what I would expect to see in the case of my lab. And we can, of course, use any of these options to scan against specific ports as well. If we don't want to go through an entire port range, we can narrow it down very specifically. For instance, if we're interested in seeing if FTP access is available on a target, and we want to do a full open TCP scan to check that, we could say nmap-s capital T-P to indicate the port number, and FTP uses TCP port 21. We can say -V for verbosity, 10.0.2.4. We can hit enter, and in this case, you'll see it's returned back that TCP port 21 is in the closed state, so the FTP service is not being used on this target. If we arrow up and we do the same for maybe SSH over port 22, in the case of this host, you'll see that TCP is open on port 22, so SSH is available on the target host. As we continue to gather information, another helpful thing to know is the operating system. This is going to give us an idea about how we may be able to communicate with a particular host in order to gain deeper access. Various operating systems may have proprietary or non-proprietary communication protocols that they commonly use, and that may be enabled by default. So knowing the operating system can help us tailor a vulnerability attack that's much more likely to succeed. So the first thing I want to point out here that we haven't looked at just yet is the Nmap scripting engine, or NSE. This is a library of scripts that Nmap can use to automate certain tasks. Users also have the ability to create their own scripts and share those, and there are also a certain number of those built into Nmap by default. Just so you know where those are, if I open up my file explorer here, you'll see the directory user, share, Nmap, and scripts. Inside of this scripts folder, you'll see a large list of those that are included by default within Nmap. In our case, for OS fingerprinting, I want to look at one called SMB-OS-Discovery. In fact, if we jump out to the Nmap website and we take a look at the reference guide, you'll see a dedicated section for this script listed in here. This particular script leverages SMB communication to try and detect what the underlying operating system is. SMB is a network file sharing protocol that's been around for a long time, and even though some versions of that have known weaknesses, it's still fairly prevalent on business computers. So SMB is one way that we can try to discover the operating system. Let's go back into our Parrot OS terminal here, and let's see if we can give this a try. Let's run the command nmap -- script, and then we want to call out the name of the script from the scripting engine that we want to run within nmap. In our case, if you remember the name of that script we looked at in the File Explorer, that is smb-os-discovery. And we want to follow that with the IP address that we want to scan against, which in my case will be 10.0.2.4. That's the same one we've been using previously for our scans. Now in this output, we aren't seeing any OS information here, which is not all that unusual. This particular script will try to perform SMB authentication using an anonymous account. That may work depending on the version of SMB that's running on the target or the configuration, but sometimes that doesn't work. Maybe SMB isn't even configured on the target. We can arrow up, and we can also add the -v flag to the end of that, which will give us some verbosity. It will return back a little bit more information, but still, we're not really getting anything returned here. So something else we can try is the -o flag. That tells nmap to try and enumerate the software versions which are in place on the target. So let's give that a try. Let's say nmap-o. That is a letter O, by the way. That is not a 0. 10.0.2.4, and we'll hit enter. And this time, we do see some promising results. We see that this appears to be running Linux 2.6. We also see, just FYI, that this is listed as one hop away, of course, because this is on my local virtual network. If we actually jump out to the target machine, which is my OWASP BWA virtual machine that we've been testing against, let's say uname-r, and that's going to show us the current Linux kernel version that's running inside of this machine. And you'll see that, in fact, we are running Linux 2.6.32. So that's good information. That's accurate. Let's test this now against a different target host. I'm going to go back into Parrot OS. Let me clear off the terminal here just so things look a little cleaner. Let's arrow up to our original SMB OS discovery script, and I will say this time 10.0.2.5, and I'm going to hit enter. Notice that I did leave the -v flag in place for verbosity here. Now, there are no operating system results specifically returned to us, but we do see some interesting ports open that lead us to believe that this may be a Windows-based target. In fact, we see a listing for NetBIOS over TCP 139. This is an older Windows communication method. So let's go back here and arrow up, and let's say nmap-o 10.0.2.5, and we'll hit enter to see what kind of information that this returns back to us. There we see our results pop up, and we do have a message here near the top letting us know that OS scan results may be unreliable because we could not find at least one open and one closed port. We see that this lets us know we don't exactly know what this operating system is, but the best guess is that this is a Microsoft Windows machine of some sort, and nmap has an 89% reliability rate that is given that. We can optionally use the command if we arrow up nmap-o. We can say --os scan -guess. So that's an optional command that will essentially do the same thing. So if your original attempt didn't make a guess, this will request nmap to specifically try and make a guess at what the operating system is. And of course, in our case, we do get the same results. Now, this particular target is a bit of an anomaly because I have a Microsoft Windows 10 virtual machine that I'm testing against. This is actually a developer machine. And if I open up that window, you'll see that this is a Windows 10 Enterprise evaluation. It's built for testing Microsoft Edge. So that's why we do get a little bit of a strange result from this output. Let's go back into Parrot OS here. And another option we can use to help discover the operating system is to say nmap-sv, and I'll say 10.0.2.5. I actually put in the wrong IP address, so let me stop that, and I'll say 2.5. I'll hit enter to get that up and going. So we have the -sv flag in place. That requests nmap to check which service versions are actually running on this machine. And depending on the results, that can also help reveal the operating system that may be in place on the target host. So now we see our results here, and there's definitely some interesting information. We see Microsoft RPC listed here over port 135. We also see that this is a member of a work group, which is called work group. That's the default work group in many Windows installations, and it appears to be running something between Windows 7 and Windows 10. We can also see the host name for this device, MS Edge Win 10. And again, this is, of course, a Microsoft Edge development virtual machine that I downloaded directly from Microsoft. We see the CPE as well, the Common Platform Enumeration listed as Microsoft Windows. Now, one more quick way I'll point out that you can at least get a general idea of what the operating system may be, and you might not be aware of this trick, is through a simple ping command. So if I ping 10.0.2.5, and I hit enter, and I'm going to stop that ping, then I'm going to ping 10.0.2.4, just so we can contrast these two results. So notice in the first one, my TTL value, the time to live value, notice that at 10.0.2.5, which is my Windows machine, the TTL value is 128. The TTL value is the maximum time a packet can remain in the network before it's going to be discarded and considered dead. And with Windows 2000 and newer, the default value is 128. With Linux and other distros based on that, the default TTL value is 64. And in fact, if we look at the results from 10.0.2.4, which we know is a Linux machine, we do see a TTL value of 64. So that's a general way that we can get an idea about what that operating system may be. Also, I will just mention in passing that if you see a TTL value of 255, there's a likelihood that you're interacting with a Cisco iOS device. That's the default value for many devices like a Cisco router. Security devices such as IPS and firewalls can pose a significant problem when we're performing scanning techniques. Next generation security devices have gotten really good at detecting things like Nmap scans because these methods are known to be the first sign of an incoming attack. However, we do have some options that can help us to evade these devices. Now, I will offer a caveat here that there really is no one catch-all solution for these evasion techniques. It takes a lot of patience and quite a bit of trial and error if you're going to get around one of these devices. So this definitely isn't a comprehensive look at how to evade IPS and firewalls, but I do want to offer a survey of some of the most useful and effective methods for that. As you continue your learning and as you practice real-world activities, you'll most likely develop your own methodology for this and discover some new things that will work. So the bottom line is, it takes a lot of practice and it takes a lot of experience to do this well. In order to see this in action, let's actually open up Wireshark. This Wireshark application, by the way, is built into Parrot OS. I already have that loaded here, and you'll see that we have the ability to capture on one of our adapters. I'm going to go ahead and capture that on my local virtual adapter here, and eventually we'll see some traffic start to trickle in as that is captured. Wireshark will allow us to see in-depth information about our traffic. So in my case, I'm going to go ahead and capture everything passing over my local adapter in Parrot OS. So we've started our capture. Let's go back into our terminal and let's perform something really basic at first here in Nmap. We'll just say Nmap 10.0.2.5 to point that to our Windows host. And if we go back in Wireshark, I'll stop the capture to keep that from continuing to scroll. And if we look at one of these, we see the source 10.0.2.15. That's my Parrot OS. The destination 10.0.2.5. That's my Windows machine. And we see that's using the TCP protocol. Now, if we look in the second window where we have the ability to drill down, a couple of things I'll point out here. Number one, we see the fragment offset is set to 0. The fragment offset field tells the device which is receiving the packets how those should be reassembled. In other words, with packet fragments, it provides an order for the reassembly. If we look at the flags section of that, just above this, we see that all of the flags here are set to 0. So this indicates that we're not using any packet fragmentation at the moment because those are all set to 0. If we were using fragmentation, you would likely see a 1 in this flag, letting the device know there are more fragments on the way. Let's go ahead and reset this Wireshark capture. We'll restart that. And let's go back into Parrot OS in our terminal here. And one way that we can evade detection is through packet fragmentation. So let's say nmap -f. The -f flag says we want to use packet fragmentation. And I'm going to, again, point that to 10.0.2.5. I'll hit enter. And let's go over into our Wireshark instance. And I'm going to go ahead and stop our capture so that we don't continue to get information. That'll make it a little easier than scrolling through that. And let's begin to take a look at some of this. If we look on the left-hand side, you'll notice that there is a number column. These are our frame numbers. So let's look at frame number 8018 for the time being. If we click on that, you'll notice, by the way, in the info field, we're told this is fragmented IP protocol. So we do see packet fragmentation happening. And in the bottom where we can drill down, notice the flag this time is set to 1. It's set to let the device that's receiving the frame know there are more fragments on the way. Again, this fragmentation makes it tougher for IPS and firewalls to detect what Nmap is trying to do and can often allow the traffic to pass through when maybe a normal Nmap scan isn't working. Nmap is going to split the packet into smaller pieces. If we look here in this output again and we go back into the next frame down, which is 8019, before we change frames, I'll also point out the fragment offset is set to 0 for this frame. For 8019, the fragment offset is set to 8. For 8020, the fragment offset is set to 16. So again, this is providing an order for reassembly. So these 3 fragments would be reassembled by the target host, and it would know which order that those should be reassembled in. In fact, if we click on one of these fragments and we scroll down in our second window here just a bit, we're even told this is a part of a fragmented IP4, and these are reassembled in frame 8020. So we can see that 8018, 8019, and 8020 all belong together and are all part of a fragmented IP protocol. And if we look at 8020, which is the last frame, you'll again see these 3 IPv4 fragments listed here. We can see the payload for each of those at 8 bytes each. So the fragment count is 3, the reassembled IPv4 length is 24 bytes. So that's one method we can use to evade these types of security devices. Now, most next generation security devices are intelligent enough to detect fragmentation these days, so we may need other methods. Another option is to decrease the MTU size, the maximum transmission unit. So instead of allowing Nmap to fragment those into 8 bytes, as we just saw, we can set that to a value of our liking. So let me go ahead and reset this Wireshark capture, and let's go back into our terminal here. And we can also say Nmap --MTU. That allows us to set the MTU size manually that we want to use. Now this must be a multiple of 8. And in fact, if I say 4 here and I go ahead and say 10.0.2.5, we're going to see an error. Let me hit enter. And we do see that error letting us know the payload must be greater than 0 and a multiple of 8. So let me arrow up and I'll change the MTU in this case to just 16 as a test. Let's go back in Wireshark. We can stop this capture and we'll go to the bottom of our output. And this time, if we take a look at, let's say, number 2211, you'll see that this is in fact fragmented. If we scroll down in our window, it lets us know this was reassembled in 2212. And if we look at the summary in 2212, we can see 2 IPv4 fragments, a payload of 16 bytes, followed by the leftover, which is 8 bytes. So the total was 24 bytes. This can sometimes be enough to fool the security device into not recognizing Nmap traffic, but realize that this will cause an IPS or a firewall to work harder and to use more CPU resources because more data has to be processed as it's receiving more data and reassembling that. So often these devices are configured to skip fragmented packets altogether. Another tool we can use within Parrot OS is called hping3. This is essentially a more advanced version of the ping command. But whereas ping only supports ICMP, hping can also use TCP and UDP if we want to as well. Let's go ahead and reset our Wireshark capture. And we'll go back into our Parrot OS terminal. And to use hping3, we can say hping3, and I can say -1. The -1 indicates we want to use ICMP mode as opposed to maybe TCP or UDP. We can also set the number of packets we send by saying -c, lowercase c, for the count. I can set that to 1, and then maybe I'll point that to 10.0.2.5, and I'll hit enter. And you'll notice that we only transmitted one packet and we received one packet. If we go into Wireshark, we can actually see that happen here. We can see our echo ping request coming from the source 10.0.2.15. Let me stop this output because it is scrolling on me. I'll go back up to the top. The echo ping request came from us at 10.0.2.15 over to 10.0.2.5, and we had a single echo ping reply coming from 10.0.2.5 and going back to us. By the way, if we go into our terminal, this hping tool is quite extensive, so if you want to see a list of those helpful commands, you can say hping3 -- help, and this is going to output all of your optional parameters and the usage for this tool. So lots of different options are available there. It's quite extensive. Now, as a more advanced example, let me go ahead and reset our Wireshark so that it's capturing once again. We'll go back into our terminal here. Let's say we want to test against the well-known port for HTTP, which is port 80. When we establish a TCP session like this, as we've discussed previously, this uses a three-way handshake. Remember the half-open scan we performed in an earlier video? That's something we can use with hping3 for testing as well. So let's say hping3, we'll say -S. This sets the send flag, meaning we're going to send a send packet. That's the first step in the TCP three-way handshake. So in other words, we want to only send this send packet to the target. Let's say -c1. Again, that will set the count to only one packet. We'll say -s, which will allow us to set a source port. Now, this is optional. We don't have to do that, but we can certainly do that if we choose. So let's set that to maybe 50/50. And then we can choose a target port by saying -p, and we'll say port 80. That is the well-known port for HTTP. And finally, our target, let's use our BWAVM at 10.0.2.4. We'll hit enter. We do see we had 0 packet loss. That's a good sign. Let's go into Wireshark. We stop the capture here, and we see our results. We see that starting right here, where we had our source 10.0.2.15 reaching out to 10.0.2.4. We see our source port was 50/50 going out to destination port 80 with a send message. Below that, we see the response from the target 10.0.2.4 coming back to us, again using TCP. That port was 80, going back to our port 50/50. That's the send ACK message we received back, which is the second step in the three-way handshake. And finally, indicated in the red highlight here, we see that we sent a reset message to cancel the TCP session establishment. All of this lets us know that our target port 80 is in fact open and able to accept connections for HTTP. And we've done that in a less intrusive way so as to hopefully evade a security device. A few other tactics to mention here in case you run across devices which may be blocking specific geolocations, or maybe specific IP address ranges, or maybe you just want to hide yourself better from the target network. Nmap actually has a built-in decoy option. Now, this might not stop the security device from realizing that a port scan is happening or some other similar action is happening, but it can make it more difficult for them to determine which IP address you're using because it hides your address within a set of decoy IP addresses. So let's go ahead and reset Wireshark to begin capturing again. Let's go back into our terminal here, and we can say nmap dash capital D to indicate that we want to cloak ourselves with decoy IP addresses. We can generate random IP addresses if we want to do that by saying RND followed by a colon, and we can indicate how many random IP addresses that we want to use for a source IP scan. Let's say 5 in this example, and the target will be 10.0.2.5. We'll hit enter. Let's go over to Wireshark, and I'll go ahead and stop the capture. And you can in fact see that we do indeed have 5 different IP addresses which are reaching out. We have our actual IP address, and then followed by 4 random IP addresses. And if we look through this capture, we'll see those repeated over and over and over. So these, again, are randomly generated IP addresses that have been created by Nmap. Now, we can also manually specify any IP address we want. Let's start a scan. Let's go back to our terminal. And if we want to manually specify that, we can say nmap dash capital D, and we can follow that with a list of IP addresses separated by commas that we want to use as decoys. So let's just say 1.1.1.1, comma, 2.2.2.2. We will then space and indicate our target, 10.0.2.5. We'll hit enter. Let's jump over to Wireshark and take a look here. I'll stop the capture, and we see our actual IP address followed by those 2 IP addresses that we manually specified as decoy IP addresses. Those are listed in the source of the traffic. We can also completely spoof our IP address using hping3. Let's go and start this capture once again. Go back in our terminal here, and to use IP address spoofing, we can say hping3. We can say dash lowercase a, which indicates we want to use a spoofed IP address, and we can indicate what that should be right after this flag. Let's say 3.3.3.3 in this case, and let's use our TCP half open command that we used earlier. Let's say dash capital S to set the send flag. We'll set the count to 1, and the target is 10.0.2.4. Let's hit enter. We had 0% packet loss, and you can see here in Wireshark that we do in fact see the source of 3.3.3.3 reaching out to 10.0.2.4. So we have essentially spoofed our IP address. And that same source that we used, the spoofed IP address, is what was used as a response on the target side. You can see that that responded to 3.3.3.3 as well. A few other options here to mention are things like free proxy servers. You can find these online, and these will make your traffic more anonymous by routing your traffic through a chain of proxy servers in order to cloak your IP address. One of the popular ones I'll mention here is Proxy Switcher. This allows you to download an application in order to do that, and you can find tons of free options online through a quick search. You can also leverage things like VPNs to hide your traffic as well. Again, many of those are freely available through a quick search. If we want to make sure we have an accurate picture of a target network, the best way to do that is by creating a network map. So let's talk about some options for that. First of all, why would we want to do that? Well, there's so much information that we're eventually going to gather that the best way to organize that traditionally is in a visual manner. It's going to help us understand what the layout of the network exactly looks like. So at this point in your scanning procedure, we've performed lots of tasks, and we should have quite a bit of information gathered. That's going to allow us to begin constructing a map of the network. We've already performed scans and footprinting techniques to get an idea about what the target looks like. So we want to create a visual representation of that so that we understand what we're dealing with. Now, obviously, the most simple way to do that is to simply draw that out by hand, maybe with pencil and paper. That's definitely a valid option, but there are also many software tools out there that will allow you to create more visually pleasing maps. And there are also automated options that can help map out a network as well to get you to a good starting point. One of those that I'll point you to here that is already installed in Parrot OS is called EtherApe. This is a graphical network monitor that can monitor your local Ethernet adapter much as Wireshark does. You can export your findings so that you have a record of those, and this also gives you a graphical representation. Now, this isn't super detailed, but it will at least get you to a good starting point to help you wrap your mind around what you're looking at. And if we just simply type EtherApe into our menu search bar, you can see that that brings up our GUI for EtherApe, and it begins capturing on the local network. And already you can see a little bit of information starting to trickle in here as it's actively monitoring traffic. We can see my machine at 10.0.2.15. Now, one thing I like to do, and this is my own personal preference, but I like to put my own machine that I'm testing from at the center of the graph. And to do this, we can click this Preferences menu, and you'll notice that there is an option for a central node listed here, and that central node is my local IP address, 10.0.2.15. So we could simply put that in there and click Save to set ourselves as the central node so that we can see all of the connections coming from the machine from which we are testing. You can also choose which interface is capturing traffic here by going to the Capture menu near the top, and if we click on that, you'll see an interfaces option, and by default that goes to my Ethernet 0, which is my local adapter, so that's just fine in my case. Also, by the way, the mode you could also change. It defaults to IP, but we could also use TCP or link layer. So with this actively capturing, as you can see, it's actively updating this network map. Let's go into my terminal here and let's just run an nmap scan against 10.0.2.0/24. We'll run that against the entire subnet. And let's go back into EtherApe and we'll give nmap just a bit of time to begin doing its thing. And you'll see that we have information already being updated here. So we'll give that just a bit, and then I'll go ahead and just pause this capture so that we don't continue to get an overwhelming amount of information. And again, we see a map with myself in the center and the devices to which I am connected. We see 192.168.0.1, which is the default gateway on my local network. We see 10.0.2.4, which is, of course, my OWASP BWA VM, and we see 10.0.2.5 as well, which is my Windows machine. And to show you how this capture updates in real time, let's go ahead and restart the capture, and you'll see 10.0.2.4, again, the OWASP machine, and 2.5, the Windows machine. At the moment, there's no line connecting those, so let's actually go out to my Windows machine. We have that up here now, so let's open a command line prompt. And by the way, as I open this machine and begin working in it, you can already see some updating happening here from that particular machine where it's reaching out to various internet locations. So back in Windows, let's just ping 10.0.2.4, which is the OWASP machine. And inside of EtherApe, you'll see a connection between these devices. Also, it has grabbed the host name OWASP BWA, and we see that connection between those, letting us know that these devices can communicate with one another. Now, I'll also point out that we can change the refresh settings here to keep the information around longer, because you will notice that this does update quite frequently. If we go back to our preferences menu and we choose the timings tab, you'll see a diagram refresh period. You'll also see options for node and link timeouts, along with the option to globally set that. So you can change the entire diagram refresh period. If you want to save this, you can simply take a screenshot of this graphical output, or we can go to File and Export, and we can export that as an XML file as well. So although this is a helpful starting point, you might want to take this information and make that look more presentable or maybe streamlined. So I will point you to a couple of other resource tools that we can use. One of those is found at draw.io, and that redirects to apps.diagrams.net. This is a free online tool that you can use, and let me actually close out of this window so you can see the main landing page brings you to an untitled diagram. You can go to File, you can go to New, and then you can choose the type of diagram that you want to create here. Let's say we want to create a network diagram, and we have several visual options for creating one of those. If I go ahead and choose one of those styles and click Create, it's going to drop in some default settings here for us, and you can see the way that these icons look. So a little bit more streamlined, a little nicer looking than something like EtherApe. A few other options for this. Some of these are paid, some of these are free trials, some of these are completely free. This draw.io is completely free, but some popular options. Glyphy is a popular option for that. That will allow you to create visual representations of a network map. We also have Lucid Chart, which you can sign up for free, and I believe that comes with a free trial, or you can pay for more powerful features. And we, of course, have the standard that's been around for quite a while, which is Visio. Now, in addition to these, there are also, as we looked at with EtherApe, with its ability to scan and automatically create maps, there are applications that will do this in an automated manner as well. All of the ones we just looked at in the browser will require you to manually create these maps with the information that you've gathered from something like Nmap, but there are applications such as Net Surveyor and NetBrain. Spiceworks is another popular one, and of course SolarWinds. All of these work in the same manner as EtherApe, and will go out and scan a target network and create a visual representation of that. I want to reiterate here that there's really no wrong way to do this. This is mostly a personal preference. The main thing is make sure all the information that you've taken time to gather, all of that useful and valuable data, make sure you're cataloging it in some way, in a way that makes sense to you, whether that's a list output of these devices, or I would recommend actually doing both. Actually keeping a list of all of the devices that you found and creating a visual representation of the network, which will allow you to see things like where firewall placement is, or where other security device placement is, which devices can communicate with one another on the network. All of these things are going to make your ongoing assessments much more easy. And additionally, when you finish your assessment, something we'll talk about later in this course is presenting the results to a client. Having a visual representation is going to be very helpful when you're giving a presentation of your findings.